All right, so we're wrapping up chapter 4. This is part 3. We're looking at our structure and function of fibrous proteins, and then the structure and analysis of globular proteins. So if we think about protein tertiary structure, this is what refers to the overall spatial arrangement of atoms in a protein. And these can be stabilized by numerous weak interactions between amino acid side chains, so hydrophobicity, polar interactions, and they can also be stabilized by disulfide bonds. And it's important to recognize here that these interacting amino acids are not necessarily right next to each other in the primary sequence. So we're going to be exploring fibrous and globular, or water or lipid soluble. So if you take a look here, one of the things that we see is this interaction between a single strand, and multiple strands, and we can actually see the way that those interact right here from a top-down view in terms of D. And we think of that as fibrous proteins. And a really good way to think about it is, does it form a strand, right? Could you braid it into a rope? Whereas if we compare that to water-soluble globular proteins, right, these look very different. They do, in fact, look like globs. And so if we're talking about fibrous proteins, then we're looking at alpha helix, typically cross-linked by disulfide bonds. We're going to see some form of beta conformation, collagen, triple helix. These are examples of the structure. And then if I think about the characteristics, well, if it's alpha helix, it's going to be tough, it's going to be insoluble, varying hardness or flexibility, as opposed to a beta sheet or a beta conformation, which is soft and more flexible. And then the collagen is a very high tensile strength, but no stretch. So these are examples then of where we find these proteins. So the alpha keratin of hair, feathers, nails are all alpha helices. Whereas silk is an example of a beta conformation, and the collagen that we see in tendons or a bone matrix would be an example of the collagen triple helix. So if we think about alpha keratin, it's a coiled coil of an alpha helix. So if I tilted the helices roughly 20 degrees relative to each other, then it makes it possible for the R groups to pack together rather nicely. You can think of it as a heptad repeat. Another way of saying that is HPXX, HPXXX. And so we have these two-chain coiled coils, or a protofilament becoming a protofibril. So a good way to look at that is, we have the individual cells, and then we have these interactions that strip really to avoid water. And so you can actually see, here's your alpha helix, there's your two-chained coil, this becomes your protofilament, which then becomes your protofibril. And so one of the things that's useful then to think about is the fact that these really are born out of a hydrophobic residue, 2 amino acids, another hydrophobic residue, and then 3 more amino acids. If you think about then the way that permanents take place in hair, really what you're doing is breaking disulfide bonds and then reforming them, to stabilize the curl. And obviously then you can lose those and reform them, if you set the curl and then oxidize. So this is one way of being able to manipulate those disulfide bonds. Whereas if we look at the structure of collagen, so this is connective tissue. You see it in tendons, cartilage, and your bones, and the cornea of your eye. And these collagen chains are long, glycine, proline-rich, left-handed helices. And so if you had 3 that intertwine into a right-handed superhelical triple helix, this triple helix has higher tensile strength than a steel wire of equal cross-section. So it's incredibly strong. Many triple helices then can assemble into a collagen fibril. This is what we can see here. This is what we mean by a fibrous protein, And this is your triple helix of collagen. And if you actually look at the collagen fibrils, you can actually see the heads of the collagen molecules and look at then a subsection of that to actually see the structure of that triple helix again. Now, it's useful, I think, to think about these 3 left-handed helices that wrap around each other in a right-handed spiral. So it's usually the sequence of repeats of glycine pro or hydroxyl proline. And the glycines are at the core of the bundle, so there's no room for other side chains. The amide nitrogen of each glycine then donates a hydrogen bond to the carbonyl of its neighbor. This results in a very rigid structure. If you think about the 4-hydroxyproline in collagen, this is what forces the proline ring into a favorable pucker, and it offers more hydrogen bonds than between the 3 strands of collagen. So the post-translational processing is what's catalyzed by prolyl hydroxylase, and it actually requires alpha-ketoglutarate, molecular oxygen, and vitamin C. So you need vitamin C in order to be able to form these key components of collagen. So this is your endoproline, this is your exoproline, right? That's the hydroxy now because of that interaction. So this vitamin C has a really key role in that for the prolyl 4-hydroxylase, it actually restores the iron 2+ state. So here's your proline residue, here's your alpha-ketoglutarate. You can form this 4-hip residue plus succinate. Right? You can also see that in terms of alpha-ketoglutarate and ascorbate going to succinate and the dehydroascorbate. If we think about silk, silk is actually very different. So silk is made up of beta sheet. And one of the things that we're going to see there is, right, we have these stacked beta sheets. So small side chains, alanine, glycine, allow this really close, beautiful packing. And the structure is going to be stabilized by hydrogen bonding both within the sheets and then London dispersion interactions also between the sheets. So a really great way to think about that is this ability to kind of stack, and you can actually see the directions here of the sheets themselves, and you can actually see the interactions then between those sheets. So this is an anti-parallel beta sheet, and you can see the role of both the alanine and the glycine within the context of this sheet. So spider silk, for example, is used for webs, egg sacs, and wrapping prey. It's extremely strong material. It's actually stronger than steel. It can stretch a lot before it breaks, and it's a composite material. It's both crystalline parts, which are rich in fibrin, and then rubber or stretchy-like parts. So that gives you a sense of the way that tertiary structure and secondary structure contribute to the different functions of proteins, largely derived based on their structures. Thanks.